Greetings and welcome back. We are in the session 6, data preparation or data pre-processing. We would like to work with the data that we have, the raw data that we have collected. And now we are going to go through some of the slides and introduce you to some simple concepts. The complex concepts I would like you to learn on in the follow-up sessions and in the follow-up courses. For now, let's just introduce you to some of the basic terminologies. Data reduction, this is rather simple. We have spoken of this in the remedial sessions, where the remedial session were referring to vectors and vector operations. Generally speaking, you might have a data that is data set that is called capital V. Capital V means a data set. A set could potentially be just a horizontal set. It could be or row or a vertical set or column, or it could potentially be a collection of horizontal rows, and that would be a matrix. I refer you to those remedial sessions, and then we would like to map them to something else. We are going to do this in a linear way. It's a lot simpler for us to discuss linear mapping of any kind compared to the nonlinear mapping, which is left for the advanced courses out of the follow-up courses we will be discussing. You have, for example, two small vectors, x and y. The linear mapping has some properties. One of the properties is that whatever you do on x plus y could potentially be the accumulation or the summation of the same mapping on x and the same mapping of y, and you simply add them up. The second property you could potentially think of is a scaling property. If you say I have x and I want to have it scaled by lambda, it is as if that you take the lambda and you simply take a look at the mapping you have done on that x alone. These are the properties of linear mapping, and it's really simple to apply. I want to show you some of the stuff pictorially. Generally speaking, imagine you have a vector, say this is the red vector, and then you have the green vector, and then you could potentially add them up, and if you add them up, there is going to be a vector right here. It's going to be right here. So if I'm looking for the vector which is going from this origin to this final point, instead of analyzing this vector, I could potentially analyze on the orange and analyze on the green. If you take a look at another example on the same picture, imagine this is your red and this is kind of a green. So this is 0 and 1 as unit vector on the y-axis, 0 and 1 as unit vector on the x-axis. You take them up and this becomes another vector. This could be twice as much, 1.5 times. This could be 3 times, doesn't matter. So you are going to have one vector on the y-axis, one vector on the x-axis, and the addition of those is going to be a vector in the 2D space. R2, we call it, the vector space is going to be R2, meaning x as in one dimension and y as in another dimension. So you could potentially have these two, and then the addition is going to be right in the middle. And the way you do it, you're considering this as a square. In this case, what happens is that you simply have this, you make this parallel with this line, you make this parallel with this line, and there's going to be an intersection, and that's going to be the vector we are talking about. The first property says instead of working with the data that is going to be perhaps a little bit difficult to handle, you could potentially decide the type of decomposition that you want and decompose that along the line of the red and along the line of the green. Most of the time, we actually decompose the vector on the x and y axis because x and y is kind of universal, easy to understand, and easy to operate and maneuver over. Now, take a look at this vector. Again, this is kind of a, you have a vector that has one on the y-axis, one on the x-axis. So this is your vector that you have. And then when we say scaling by 2, what does that mean? This vector times 2 is going to actually go all the way here. Now, what the second property says is that instead of analyzing the larger vector, you could potentially analyze the first smaller vector and then simply time it by 2. That's what this one says. So of course, it has to be linear mapping. So keep in mind, we do have nonlinear mapping, and that's going to be a subject of a different course, not this course. We want to make everything simple for this course. There is a matrix instead of a vector. We could potentially play with the matrix. We are going to have a basis vectors, as I said. For example, 1 and 0, potentially, if we consider this to be the x and this to be the y, 1 and 0 is going to be here, 0 and 1 is going to be here. So this is going to be my base. So we need to see what is the unity vector on the x-axis and the y-axis. Now, what is this one doing? It's actually mapping. So if you have this vector in mind, again, please refer to the remedial session. The first one says, I want you to expand on the x-axis twice by a factor of 2. And the second column is telling me that I want you to enhance or expand the y-axis by 1.5. Remember, this is y-axis unity vector. This is x-axis unity vector. This is the scale of the x-axis, and this is the scale of the y-axis. So as you can see, this is going to be the space or the vector I'm looking at, but at the same time, I have the luxury of mapping it. And this is going to be a stretching on the x-axis and a scaling on the y-axis. You could potentially do different numbers. This could be fraction, this could be large number. It all depends on the application and the type of data that you have. If you take a look at this, what is happening? What is happening is that you're going to actually multiply you could potentially multiply the y-axis. You see, the y-axis hasn't changed. The y-axis hasn't changed, and you could potentially, I would say 1.5, you could potentially come to this point. So your vector is actually coming to this point. There is a typo here, my mistake, my apology. So this is a vector that is coming here, and this vector is going to give you 0.5. And then, so this is 0.5 on the y-axis and 1 on the x-axis. This is correct, actually. So 1 on the x-axis. So this vector is 1 on the x-axis. And when you shadow it on the y-axis, you get 0.5. So this is correct. 1 and 0.5. So you have skewed the data, but intentionally and knowingly. And you know that you're going to do this perhaps on the entire data set that you have. So you skewed the vector that was supposed to be resting on x-axis by 1 and 0.5. So that's what happened, okay? And then the y point hasn't changed. 0 and 1, what does that mean? This is 0 and this is 1. So this point that I'm actually referring to has the coordinate of 0 and 1. 1 being the unity on the y-axis and 0 being exactly on y and nothing on the left and right. So you got one vector here and you got one vector here, and the result is going to be a vector that is going to be right here. What happened? You simply skewed the x-axis, you moved a bit, you basically rotated this, not rotation, it's a combination of rotations and basically having it on the vertical line. So what is happening, you basically create a new vector, that's your shadow, and this is your shadow on the y-axis, and the result is going to be here. You could do that. One thing you need to keep in mind is that where do you want to do it? Do you want to apply to all of the data? Did you find a very important cluster that you want to do it on that cluster? So it's really important for you to decide how you want to basically map. This one, actually, we are going to skew it on both x and y axis. So 1 and 0.3. So if you take a look at this, the coordinate of this point that I'm referring to is going to be 1 being x, 0.3, 0.3 being y. So this is 1 and 0.3. And this one is going to be 0.3 and x and y, 1. So this is 0.3 here. And then 1 is going to be here. So what is the coordinate? The coordinate here is 1 and 0.3. The coordinate here is 0.3 and 1. So you have two vectors now, and then you can see that the summation of the two vectors is going to yield the results here. You're skewing on both axes. This is what I was referring to as in rotation, potentially. So, or expansion and rotation at the same time. So what you can see is that I'm actually doing a scaling on this vector, 1.4, 0.35. So that's one. So 1.4, they take a look at this coordinate. 1.4 is here, almost a shadow here, and 0.35 is going to be here. So that's your vector. And this one is minus 0.38. You actually went into the second quarter and minus 0.38, and then you're smaller than 1 on the y-axis. So this is 0.75. You got a vector here, you got a vector here, and then the result is going to be here. Okay. For rotation, that was not a rotation. For rotation, here is the rotation. This is a general rotation. When we say rotation, the shape is maintained. That's the difference. You see, I didn't maintain shape here. I skewed it. I did not scale it on both directions. And even if I had scaled it equally, that's not the same shape as what I have here. This is not the same shape that I had originally in my mind. So as you can see, these are different types of mapping. This one is very simple. It simply says, why don't you rotate everything you have? So this is what it is, and then rotate. Exactly the same shape, the same angle, the same size, everything the same size, rotate. So what is this? There are some matrices that actually achieve rotation with the angle of theta. This is a very famous matrix, both for two-dimensional as well as for three-dimensional. There are different types of rotational matrices, but these are well received by the community. So what is it? You have originally you have this, and then you have this. So originally you have X and Y. When you multiply it by this matrix, you're actually rotating your entire axis, the two axes, by theta degrees. So you go to X prime and Y prime with a little hat on the top. So this is a Y prime hat and Y prime hat and X prime hat. So rotation is different than scaling we discussed last time. Rotation, you maintain exact shape. You simply rotate. And when you rotate, you're supposed to be able to basically represent the data in the new axis, So if you happen to have a vector here, if you watch my cursor, this is your vector. Let's go back. If you have a vector here, this vector, right? This vector, and I want to rotate this by theta. So this is supposed to be 2 and 2. So I'm going to say 2 and 2, right? So open bracket, 2 comma, open 2 and then close bracket. If that's the coordinates of your vector, all you have to do is to multiply it from the left to this matrix. And if you do it, it's going to actually rotate by theta. Now, this one is different. You do have the X and Y and Z. The type of mapping we are talking about, the rotation we are talking about, it says, I don't want you to change anything on the X-axis. X-axis remains the same in the new R3 space. Remember, we are mapping the space. This one is R2 space to R2 space. This one is R3 space to R3 space. And in this rotation, I'm saying I don't want you to change anything on the X-axis. X-axis remains X, whatever it is. And the Y is going to have a theta here. So it's going to have a theta here, and then it's going to be Y prime, and a theta here is going to be Z prime. So the bottom of the space, which is YZ coordinate, is actually rotate this way. There are different types of rotation matrices, but these are simple stuff, and we wanted you to be aware of it, okay? We could potentially define different bases, coordinates. Now, if you take a look at the Euclidean space, in the Euclidean space, you have this as your unity vector. You have X-axis, unity vector on the Y-axis, unity vector on the Z-axis, and you have a point X, Y, Z, and that is 2. I would say that is going to be 2 and 3 and 4, for example, right? Now, you could potentially decide that your bases are not scaling. They are not rotational. You simply find your basis coordinates in a very interesting way, which is not the topic of this class. I'm going to show you some of this stuff very quickly. So what happens is that you could potentially decide that your X and Y and Z coordinate are potentially going to go into their space, and you have different axes. And if you have different axes, your vector is going to be represented by these basis coordinates. So this is going to be your new X and Y, and this vector is going to be represented differently. You could potentially do so considering the basis coordinate and then represent, for example, every point according to the vector. We do have ways of finding the basis coordinates. One of them is famous, it's called eigenvector and eigenvalues. And we would like to discuss that in a separate topic, separate class, separate session possibly. So I'm going to leave you with these slides. You could potentially go and learn eigenvalue and eigenvectors. Okay. Now there is another one, PCA, principal component analysis. Search it on the website, and what happens is that you are going to come back with the basis coordinates. So the entire idea is that can you potentially create a new basis coordinates, and that's what it is. We have different topics on the random sampling here, and then a nearest neighborhood. We spoke of nearest neighborhood in the past. I don't want to go through these stages. You could see these are the classification techniques, and we have them for the, you could potentially take a look at this. For example, if you remember in previous parts, we spoke of this. We want this to be minimize the dissimilarity. We want these to look very much the same. We want this to, again, we are going to go through the KNN and K-medoid in future slides, but generally speaking, the rule is simple. The rule of thumb is very simple. We are trying to classify, and we are going to put these data together. And the reason we want to put them together, because they look alike. They belong to the same religious belief. They belong to the same political views. They belong to the same profession or career. They belong to the same geographic preference. For example, near the river, near the mountain, at the bottom of the mountain, at the top of the mountain, on an island. You know what I mean? So it depends. So you're trying to make sure that the points you're going to put together, they're going to have as much similarity as possible. Or in other words, you want to minimize the average dissimilarity. That's what you want to do. Again, these are the topics we will be talking about. I want to also quickly go through text processing. This is part 6. And if you remember, we had 2 labs on text processing that you have successfully submitted recently. What you need to know is that when you do text processing, you need to be aware of a number of concerns. Do you want to remove them? Do you want to interpret them? And how do you want to interpret them? We know that some of the text components, words, sentences, they may be lowercase versus higher uppercase. Remember, the computer does not understand anything, and the way you are going to do it is that the way you are going to do it, you are going to for example, they say lowercase. So lowercase for computer has a different binary representation. Higher case, uppercase has a different binary representation. So when you're talking about it, the question is, how do you want to deal with the uppercase, lowercasing? Do you want to consider punctuation? Do they mean anything to you? Stop words, there are some stop words, some of the things we are going to discuss and show you some in a moment. Frequent words, there are things that I'm going to repeat. You can see from my verbal communication that I often and frequently use a specific word that became part of my habit. You could potentially see that I don't use some of the words all the time. They became rare occurrences in my communication to you. Do you want to consider them important? While it says removal, keep in mind, you don't have to remove them if that's not your policy. If that's not your rule. You need to basically come with the rule that you, emojis, do you want to consider emojis? Do they reflect any meaning? Do they reflect any emotion, any sentiment? Do you want to remove them? Do you want to consider them? Do you want to convert emojis to words? We usually have a lot of links we provide, URLs, HTML tags, and then you have chat words conversion. I'm going to show you some of the wording, spelling correction, and so on. Now, take a look at this. For example, when we talk about punctuation, are these going to be important to you? Because they are. On Twitter, they are. On WhatsApp, they are. On Facebook Messenger, they are. Do you want these? Are these important to you? Me, my, I, myself, I, our, ours, things like that. Basically, walks and walking is counsel and counseling. Are they supposed to be one thing? One meaning to you? How do you want to map that? The variety of the wording that you have, the synonymous words that you have, synonymous words that you have. How do you want to map that? Are you going to map that to just one understanding, or are you going to separate them? For example, in French word, and I'm referring to my memory, which I'm not sure is going to be correct or not. In French word, many of the words are actually dedicated to gender. So there is male and female words. You could potentially decide that they all mean the same thing to you anyway. Basically, what does this mean to you? You need to make a decision. What does this mean to you? And there are mistakes here, right? So this one, you can see that there is a question mark here. It wasn't even supposed to be there. And this is a mistake I did. And it happens when you type a text on WhatsApp, on Twitter, on Messenger, whatever, you could potentially just push a button and it goes there, and you are in rush, you simply submit it, and suddenly you realize you made a mistake, a simple typo or something, right? HTML tags, chat words conversion, in my opinion, it is IMO, very much used, quite often, frequently, in my humble opinion, IMHO, humble opinion. Thanks, often we don't put the A inside. We simply say THKS sometime. So you need to see whether that's something you want to consider or not. These slides are meant for you to basically hear them for the first time in this class, but they will be actually discussed extensively in the follow-up classes. So I hope we had the opportunity to familiarize you with some of the keywords in this class. For now, let's stop now, and then I'll take you to the next level, which is going to be the image processing as well, slide image processing.